Enjoy.
Thank you very much for the introduction. So yeah, as Mr. Hopper already said, I'm from a research institute. It's called Fortis. It's located in Munich in Bavaria. And actually, I am doing my PhD together with the Technical University of Munich on the automatic configuration of TSN. But today I'm actually not here as a kind of scientific researcher. I more or less do knowledge transfer. So I will not discuss scientific crazy theories with you. I will actually try to explain, as already introduced, what TSN is, why it is interesting for the OPC OA community, and also what the current challenges with the configuration of TSN networks are. So let's dive right in. So my first slide actually is there to get everybody on the same page and introduce to you what time-sensitive networking TSN is. So TSN, to make it short, is an IEEE standard extension for Ethernet, which provides additional features. Features, for example, like determinism, and we already heard a lot in the other presentations today. We have real-time capabilities which are added to the Ethernet standards. TSN is very interesting because it is vendor independent, and also it supports the Convergent Network, and what that is I'll show you in a minute. So the idea of, also to make it clear what determinism and real-time is, so determinism from a networking perspective just means that you can actually guarantee the transmission of packets. So if you send it from A to B and the network is appropriately configured, the network will make sure that this packet is transmitted. And real-time is, on top of determinism, that you can not only guarantee the packet transmission, you can also guarantee it with a specific timing requirement. So that's the basis. So why is this time-sensitive networking standard interesting for OPC UA? Well, as I said, TSN is located on the second layer of the OC model. So if you look into the higher layers, you of course find somewhere the OPC UA specifications and protocols there. And the cool thing about that is actually that TSN provides the infrastructure to like for the existing Ethernet-based protocols to like get these features which adds to the current Ethernet standard. So in the end, what it does is TSN will make OPC UA deterministic and real-time capable, because OPC UA is an Ethernet-based technology, and TSN is adding new features to the Ethernet stack. So that's the overall idea. Also, what I usually do is I provide two short bullet points about what is TSN not, because there are plenty of misunderstandings, as also already said. TSN is not an application protocol. It is standard Ethernet, meaning an extension of standard Ethernet. And TSN is also not a new field bus protocol, but it provides the infrastructure for Ethernet-based protocols. Again, making, for example, OPC UA real-time capable. So the next slide is actually about one of the key features that I think is most important for time-sensitive networks. It is the convergent network. So what is a convergent network? A convergent network is the combination of traffic with different requirements over the same network cable. So what you can see here is actually on the left-hand side the Ethernet cable. And on the right-hand side, you have different streams, network streams that have different requirements. And the idea of this convergent network is actually to transmit these requirements on the same network cable. So as you can see, you could have broadcast video traffic, you could have safety traffic, you could have streams which are really very high requirements on latency and jitter, for example, and you also have high throughput data that in the end can be transmitted over the same network cable. So that's the idea of the convergent network. Of course, this new technology, or like this idea of putting everything together, raises the complexity level to a new dimension, kind of. How does TSN cope with these kind of convergent networks? First of all, maybe to say TSN is not a single standard, but it provides several standards, and I don't have the time to go into details of each and every of these standards. The idea is that there are different standards, for example, for scheduling. So you have scheduling mechanisms. There are standards in the TSN family which are for reliability, mainly to support and provide redundant components in your plant for higher availability. There are standards for tight time synchronization, and you also have standards for the configuration, of course, of these networks. And then there is a third, and from my perspective, very interesting new trend. It is the profiles, the TSN profiles, or industrial profiles. So the idea of these industrial profiles is actually that the industry, for example, the IEC 6082 or IEEE 6082 is there for the industrial automation domain. And they are basically analyzing different use cases from the domain and try to recommend you specific kind of combinations of different standards that you could use for specific use cases. So the idea in the end would be to have kind of some building blocks. And the good news with it is that there is, based on the use case, you can combine different kinds of these standards, and you don't necessarily have to implement all of them. Okay, so what I want to do now is basically show you two standards. So the first one is a scheduling mechanism as an example, and then I will go a little bit deeper into how real-time networks based on TSN can be configured. So let's dive right in with the 802.1 QEV, or as it's commonly called, the TimeAware Shaper. The TimeAware Shaper is a scheduling mechanism, so it makes sure that your packets or your streams are transmitted in a specific manner. It's a time-triggered approach, and what you basically do is you take all the bandwidth on a specific port which is available, you cut this bandwidth into cycles of equal length that you can see here. These cycles are repeated over and over again. And then you basically reserve slots inside this cycle to make sure, or slots based on the priority of specific streams, to make sure that, for example, if you look at the slot for priority number 1, that only traffic with priority number 1 can be transmitted on that port in that specific time frame. And of course, this is a way to guarantee that the streams that you have, if they fit into these kind of slots, are or can be deterministically transmitted. And also, if you change the starting point of this slot to somewhere far away from the beginning of the cycle, it has a huge influence on the latency of the streams. Okay, so this as an example, I will come back to that actually later. Now I want to show you the different kinds of approaches and for configuration. So the idea is these approaches can be used to not only configure the scheduling mechanism that we just saw, but also the convergent network, which would be a combination of these different kind of scheduling mechanisms and other TSN standards and features. So there also is a standard for configuration of TSN networks. It is the .1 QCC, which basically describes 3 different approaches. We have a centralized approach, we have a distributed approach, and there is a kind of a combination of both, the hybrid approach. And what I want to do next is I want to go a little bit more into the details of each of the approaches and show the current challenges. And the end of the talk will basically be a comparison between both of the centralized and the distributed approach. So let's dive right in. So what is the usual setup? Typically you have some kind of talkers and some listeners. And in the middle you have some bridges to transmit real-time traffic, for example, OPC traffic over TSN. So the idea is for the centralized approach that you have 2 central entities, the centralized user configuration entity, the CUC, and the centralized network configuration entity, the CNC. And the idea of the centralized user configuration is basically to gather all the different requirements from the end devices. So there are 2 possible ways to specify these requirements. You can either as a user directly model the network, For example, the network topology, the different latency and jitter requirements, or the different capabilities of your bridges, and so on and so forth. So all these information will be stored in the centralized user configuration. And you could also directly communicate with the end devices, for example, also via OPC UA to get the requirements of the individual network devices and store them in this centralized network model, I would say, or the knowledge base. So what is the centralized network configuration entity? Well, this one gets all the user requirements from the CUC and is kind of the configuration engine of the network. So this guy right here will, in the end, generate and calculate the configuration of the network. For example, the schedules for the TimeAware Shaper that we just saw, or any kind of, I don't know, parameters for time sync protocols, and so on and so forth. Once this is done, there's a network management interface to the actual bridges, which then will be used to deploy the kind of configuration that is calculated in the CNC. And that's the general idea of the centralized approach. So what is the challenge of the centralized approach? Well, basically, long story short, it's scalability. So what you usually do with this centralized network configuration entity, you would use some kind of solver which configures and generates, for example, again, schedules for the TimeAware Shaper. So there are plenty of these kind of different technologies out there. For example, you could use SMT solvers, satisfiability modulo theorem solvers, or ILP solvers, or different kind of heuristics and genetic algorithms. So depends, again, on the use case, and I don't have time to go into details about that. But the problem with that is that if you, for example, want to do scheduling for the TimeAware Shaper, you will realize that this is an NP-complete problem, and what that means is that the execution time of this solver, meaning this central entity here, will be exponential. So what you can see on the right-hand side is actually experiments that we did using an SMT solver for scheduling the TimeAware Shaper. And what you also can clearly see is that the execution time for small networks is still all right, but yeah, it grows exponentially. So that is a problem and a challenge that is currently faced by this centralized approach. However, I'm not talking about like unsolvable problems here. It's more the general challenge, and there are, of course, some pretty interesting ideas how to solve these challenges. So going to the next model, the next configuration model, this is the distributed model. The idea of the distributed model, as you can clearly see, we have no centralized entities. Rather than that, we have only the bridges and the talkers and the listeners, and the idea is that the configuration information is not gathered somewhere central. It is, rather than that, directly transmitted on the active paths of the network. So if a talker wants to communicate with a listener, then it will basically send the configuration requirements, meaning the latency requirements that the specific stream has, to the different network devices. And once a device receives such a configuration requirements, it will configure itself. And when this is done, so for example, the talker wants to communicate with the listener, sends a packet with the requirements to the first bridge will receive it, parse it, and kind of configure itself, and then it will be forwarded to the next bridge, which will also configure itself, and so on and so forth. So you do this on every network on the path. And in the end, you will have a complete reservation of bandwidth from your talker to the listener. So again, what is the challenge with this kind of configuration model? Generally speaking is, of course, the scope of the configuration, which is limited to an individual device. So you do not necessarily have the central overview of the network. Rather that you have these kind of individual devices which have to configure themselves. And this, of course, makes some things pretty challenging, for example, the optimization. Because if you imagine that this bridge has a configuration, this bridge has a configuration, and they don't know each other, or they don't know the configuration of each other, then it's, of course, pretty challenging to optimize the overall schedule for distributed approaches. Same holds for the diagnosis. So what happens if the first, the second, and the third bridge in a row is configured correctly and the fourth bridge then suddenly is not able to configure itself correctly? So of course it can send some kind of failure report to the other bridges, but as they don't know the configuration of the last bridge, they almost also do not really know what happened there. So it's really tricky to do configuration diagnosis here. And also, currently, this approach does not scale in terms of the number of hops, like the size of the topology, and is also limited to the line topology. But again, this is not unsolvable problems. This is only current challenges that will be solved in the future. And yeah, the third approach is actually a very interesting approach because it kind of combines the advantages of the other two approaches. It is the centralized network, meaning we have a CNC, and the distributed user model, meaning the requirements do not come from any kind of centralized entity, but are directly gathered from the talkers and listeners. So this could actually be one of the solutions for being as flexible as possible and also optimize as fast as possible. But as the other two approaches are not fully understood, I would say the combination of both approaches is not yet really investigated. So this brings me to my last slide, which is the conclusion. And as I said, it's a comparison between the centralized and the distributed configuration approach. And what you see, or what we already saw, is that both of the issues have scalability challenges which have to be solved. If you want to use the central approach, you have a rather static configuration because the central solver just needs a plenty amount of execution time in order to generate the configuration for the network. But you can, of course, do optimization, highly optimized schedules, for example. On the other hand side, we have the dynamic of the distributed approach. And of course, so this is more suitable for a plug-and-play system, for a small and medium-sized plug-and-play system currently. But the optimization is very tricky. Of course, in the centralized approach, you have kind of a dedicated configuration infrastructure which is needed to perform the approach, whereas on the distributed approach, you do not necessarily need an extra entity, a server which configures and communicates with all the different devices. And also, as I said, the diagnosis for the central approach is easier because you, for example, can easily run quick schedulability tests and see whether specific requirements can be scheduled on your network, whereas this is pretty challenging on the distributed approach. So with this slide, this is kind of my take-home message. So if you slept throughout the whole presentation, now's a good time to wake up again. Yeah, thank you very much, and I'm open to questions. You can also approach me after the talk, of course. And also, maybe to emphasize this a little bit more, of course, we are a research institute, and if you are looking for collaborations regarding time-sensitive networks, you can just approach me after the talk. Thank you.